meeting of the Math Club, and today we have our guest speaker. His name is Dr.Balaram Ghimire. He is an assistant professor at Alabama State University. So today he will be giving a talk on numerical solution of elliptical partial differential equation using Chebyshev polynomials. I hope you will enjoy his talk. Thank you. Yes, welcome.
Thank you. Good afternoon, everyone. Thank you very much for inviting me for this talk. I'm very honored to be here today. I'm Balaram Ghimire. I'm an assistant professor of mathematics in Alabama State University. I'm working on computational mathematics. Actually, what I would say is the numerical analysis leading to the computational mathematics. And my research is more about the meshless method. I'm sure you must have heard about the mesh-based method like finite element methods, finite difference method, finite volume method, etc. They are very effective and very useful and very practically applicable methods. And after, in 1990, in the beginning of the 1990s, Edward Kensan, he introduced a meshless method. Actually, he published a paper which was about not creating a mesh. Instead of not creating a mesh, he used the meshless method. So a lot of development had happened after that period. So today I'm going to briefly, at the beginning, briefly I will show you about meshless method. I don't know how many of you have heard that word meshless method before. It must be new, but still, if you have heard it, that's great. I will just give you a simple difference between the mesh-based method, meshless method, for a couple of few slides at the beginning, and then that method is used for the various purposes. And one of the application actually is solving partial differential equation. So hopefully you will enjoy. If you have any question, please don't hesitate to ask me. I will be glad. I need to, I need to take care of the time also. Please let me know when I'm done or when I'm supposed to go, because it might take a little bit long time. So here is how I start. Basically, I'm thinking to give you a few introduction about the meshless method, and then what is the application. Actually, the field that I'm working actually is the reconstruction of the data, and then applying in solving partial differential equation, of course, typical type of, not all. And then, basically here, I'm saying here, radial basis functions, that is what we're working with. And then surface reconstruction. And this is the Chebyshev polynomial scheme. That's the place where we use our research on the meshless method and a few conclusions. So let me start with the very known words, very familiar. This era is the era of less. Everywhere you see the less technology. For example, wireless. There are so many wireless technology we have so far. We'll get it. A cellular phone, wireless mouse, keyboard, and most importantly, Wi-Fi. And similarly, we always go now paperless, email, letter, bill, memo. Transparency-less, we have now PowerPoint, and similarly we have a fieldless, which is digital camera. So this is very common in this era. So we live in this era, and so this is very important. So that's why we look to do something in the meshless in mathematics as well. So mathematicians actually they created and they introduced as the very first time mentioning. The history is not that much far. As mentioned, 1990 somehow. it started. The mathematician and the researchers in the field started. So here is the, actually this is a graphical how the maze method works and what is the mazeless. And similarly, this is just one example. And this is the example here why I put this is a 3 intersecting tori. And this is one paper. This is a very, used paper. And in this paper, actually, the mathematicians were wanting to create a maze. So how difficult it is to create a maze in this case. So basically, we don't need, here, when you go to the maze list, we don't have to do it. Of course, every numerical method has pros and cons. That has, but still, they have something creating a maze. This is a maze method, and this is a maze list. This is that's we call this Stanford bunny, because this is the figure we created from the data from the Stanford University Computation Department. Actually, they create that. We can create something like this with the help of data. If we get some data, we can create such a structure. So that's the one example. We don't have anything to do with right now to relate because how we cannot go in detail with this data. So what are the data? So what are the correct numerical methods which we call mazeless numerical methods? There are so many methods. Among them, few are like smooth particle hydrodynamics. That's one mazeless method. Element-free color-free method, and so on. So here's a method of fundamental solution, method of particle solution, and radial basis function correlation. Actually, we follow in our research, we follow the radial basis correlation. So here, as I mentioned, there are so many applications. Many researchers are working in this field, which are working in different fields. So the first and foremost, the very important is, of course, the solving partial differential equation, because that's the one we use for mazeless method. And here is the one, I think that's where I work from mazeless method. And this method has other application in other fields, like in computer science or in other fields, like not only in mathematics, but in other fields like medical imaging, reverse engineering, and in so many other fields also. These methods, those specific methods, which we call the mazeless method, have been applied. So that's the part of this application here. Here, because as I mentioned you here, I want to reconstruct the data and using the mazeless method for solving partial differential equations. Those are the two fields which I worked with my advisor, with my colleagues in this field. So this is a very well-known thing, like when you want to reconstruct the functions from the data. This is how this is a very well-known in mathematics. For example, you have a given data set and you have a given functions, then you want to reconstruct the data. So to do this one, to reconstruct the data functions from the given data, we use radial basis functions. So I have not here included because I was thinking to go over only the reconstruction. But again, I changed the mind and I heard I will give you some idea about Chebyshev polynomial. So I have just given you some idea here. So here we have a scattered data fitting, and how do you use the radial basis functions? Basically, here is how the radial basis function works, because this is the given scattered data, and radial basis function will help us to reconstruct the surface. So this is one example that I just wanted to show you. And I will show you a couple of examples like that. Of course, I cannot So this looks a little bit pretty different here because this is the original. Might not be accurate, but this is the original data, and this is the this is what after we lost the data, and we want to do the RVF interpolation so we can reconstruct the data. Of course, it looks like these two figures looks like exactly the same, but that is the one which we consider as reconstructed. So it is called the image process. So what I wanted to tell you is this method has a lot of applications. If you lost the data, in that situation, we can gain and we can construct, we can obtain the original image. So that is one part. So here I talk about the RBF, radial basis function. RBF, radial basis function is just a scalar function, just like here, where lambda I is the weight of the center and phi r is the radial basis function, and we take the regular Euclidean rule. So the main idea here is the radial basis functions will give you will reduce the scalar into the scalar function, and that's why it is easy to work in higher dimension. It is easy to work with more data points, could be 1,000, 100. So that is how we define the radial basis function, and there are many radial basis functions the researchers have taken. So basically, radial comes from radius. So we take the center and we find the distance between any two points and we interpolate the data. So the idea behind the radial basis function is very simple, so it is easy to understand. So I was thinking to apply in the undergraduate level also, but still I'm trying to do it. So here, linear, cubic, multi-quadric. I think this is the first introduced radial basis function. And similarly, polyharmonic spines, Gaussian. So these are the different radial basis functions the researchers have so far used. Of course, we have the new radial basis function as well. And in messless method, we use all these radial basis functions to interpolate the data. As I mentioned, every numerical method has their own pros and cons. So, in the case of the radial basis functions also, it has some advantages, some pros and cons. For example, if you compare to the mesh-based method and meshless method, it requires neither domain nor surface discretization, because that is the one hardest part in the mesh-based method. You would take like piecewise polynomial functions on regular to do the discretization. But here we want to we just take the radius. So comparatively, when you compare with the mesh method, it looks like a little bit similar to 2D and 3D. That's why I'm saying we can easily extend to the higher dimension. And it doesn't involve many numerical integration as well. So that is also one of the advantages to the mesh-based method. And similarly, the coding part, of course, finite element also is coding, is easy and it is easy to code. Cost effectiveness is due to the cost effectiveness, it is considered good. However, there are cons of the radial basis function based system. Very importantly, many mathematicians, they consider it doesn't have good background history. So there are some cons, but when we speak specifically on the radial basis functions, selecting base center is not that easy. So that is one cause. And similarly, if you look at other multi-quadric or inverse multi-quadric, you must have seen the CD. That's a shape parameter. And we have to adjust the shape parameter to get the best accuracy. Because in this method, we use how accurate, because all the time what we do is we approximate our solution. So due to the variation in C, we have some difficulty with the shape parameter. So choosing shape parameter is really the open problem. And there are a lot of papers on choosing as well. So that's another cause. And when the data set, when you take the large number of data, then you have some problem. You have computational problem or something. So which actually ultimately lead you to the yield condition part, and you might not get solution, or that is not reliable. So those are the things which we are supposed to take care. So these are considered as an RDF methods. So none of them, as you already know as a mathematician or whatever, none of the numerical methods are perfect. Every method suffers from some conditions. So the only thing is how do you overcome, how do you tackle those problems. So even though it has some disadvantages, it's been widely used in many fields. So that is one part here. So here I just wanted to show you, because that's how the points are, data are taken. It's not my part actually. I just wanted to, I showed you a Stanford one, or I'm going to show you another. We will get data points from some computational lab or something like that. So why we use this is actually here, as I show you here. This is the laser scanned point cloud, and this is the how you fitted the surface when you use the method. And similarly, with the help of this one, you can create that kind of evidence. So that's the part. So this is another figure which we call the reconstruction of the surface. If you have a data points, you can reconstruct. So this is also, as I mentioned, with the Stanford drug. So we take the points, we take the data points from the. So this is another Stanford way. So now, this part, so far what I talked is about the reconstruction of the data. One of the applications of the MCS method using radial basis functions. But now here, I just wanted to go fast. I just wanted to go and show you how can we use the radial basis function to solve, partial differential equations. Basically, I want to solve elliptic partial differential equations. So that is the one that the title of the presentation shows. So there are so many numerical methods to approximate the solutions of the partial differential equations, and all of them they require, the expectation is to have a good accuracy, efficiency, and simplicity. So among them, as I mentioned you early, Edward Kensa, actually this is a powerful messless numerical method based on the radial basis functions, which is employed to various periods. And as I mentioned, yield conditioning and choice of set parameter are the complexity problems for the researchers in this field. So here, I just wanted to show you the two-step Chebyshev polynomial scheme, which I work with, because here the word Chebyshev definitely means I chose Chebyshev polynomial because it has a nice property. I think most of you know what is Chebyshev polynomial. So it has a very nice properties, and due to that property, I use Chebyshev polynomial as a basis functions to solve some linear elliptic PDEs with constant coefficient. So there has a two part, actually I have two step and one step. So here I just wanted to show you the two step Chebyshev polynomials. So this is just first 5 Chebyshev polynomial plots. If you plot them, you will get like this kind of figure. So this is what I'm thinking is it has a very nice properties like this. The very important property is a sequence of orthogonal polynomials, which converges very fast. That's what we call spectrum convergence. And Chebyshev nodes are used in polynomial interpolation. That is one another. And similarly, the local maxima and minima of Chebyshev polynomials on the interval -1 and 1 are exactly equal to 1 and -1. So regardless of the order of polynomials. So that's why we need to, which makes them valuable for the living PDE. So how you apply, now here comes, how we apply the CPS, Chebyshev polynomial scheme in two-step approach. Because we have I will show you a figure in. We have a computational domain and we have a boundary. So once we solve the problem, if you would like to solve any partial differential equation, we have to, solve in the boundary and the computational domain, and the domain. So in the two-step approach, Chebyshev polynomials are first used to approximate the particular solution of the PDE. Because that is the important part, because we don't know the analytical solution. So we have to go to approximate the particular solution of the PDE. Then the resulting homogeneous equations. Homogeneous equations are solved by boundary type method. There are other methods which we call the method of fundamental solution and then collocation transfer. So these are the methods which we use to solve the homogeneous equations. So I just wanted to show you how we actually use this method. Basically, this Tix and Tzy represents the Chebyshev. And we approximate the solution U with a linear combination of the Chebyshev polynomial. And when you apply the operators, take off the partial difference here. When you apply the operators, then that's what we call the collocation method. We collocate on the points inside the boundary and the domain. With the Chebyshev nodes, we get the linear system. And Chebyshev polynomials are defined only on -1 to 1, so we have to rescale the domain. So this is how we rescale. And I think this is very common for when you rescale and put it in -1 to 1 or whatever. So this is how we transfer into -1 to 1. And that's how you preserve the PDE. That's how you rescale the domain. And to preserve the PDE on that domain, actually we have to do this step following the boundary value problems in this one. So this is how you rescale the PDE. Because not only you are putting your PDE into -1 to 1, but you have to rescale the PDE. So these are some technical steps that we follow when we rescale the PDE. So this is how we do it. This is the original domain. We don't know for sure what the domain is, but once we rescale, then we transfer into this domain. So now we can apply the Chebyshev polynomials. So this is what transformed domain. Transformed domain. So in this talk, actually here, what type of problems? Because it's always important that what type of problems did we solve? So here are the few problems that we solve by using our method, which is a Schroen equation, modified Helmholtz, and fourth order PDE. Because naturally it is not possible to work with all kinds of PDE, because there are some PDE. That's what I say, these are linear elliptic partial differential equations. And then how do we validate our numerical method? What is the numerical accuracy? So here, many I think here I've seen some professionals who work in mathematics. Usually in mathematics they divide or they prove the convergency and so many things that's been done. But here we take and we perform our this numerical accuracy in the program, MATLAB. We can do anything, and we would like to see how accurate we are. So that's why in the next table you will see some numericals, numbers, which actually measure the numerical accuracy, how accurate our method is. But to get that accuracy, of course, we have to have this numerical. So for that purpose, we have calculated maximum absolute error, which is defined like this. So we find out the maximum absolute errors with to validate our numerical accuracy. So there are some technicalities. That means where did we perform our numerical experiments? So that is carried out on a unit square, and that's another amoeba-shaped, Cassini-shaped, peanut-shaped, and then star-like domains. So these are the computational domain. So some are irregular. Of course, if you go and use the rectangular negative 1-to-1, you will get maybe high accuracy, but still we are getting the high accuracy when we performed our experiments on these irregular domains. That's what we call the computational domain. So we have to take the certain number of data points. That's what we call the boundary and the test points, boundary points and the test points for this one. And similarly for the method of fundamental solutions, we have to have the fictitious boundary, because this is where we solve the boundary. So source points are located they're chosen to have the same set as that of boundary. And the source radius R is found by using Ghimire arbitrary. That's one method, which is used to get the correct set parameter. We don't need set parameter here because Chebyshev polynomial doesn't have any set parameter, but still how to choose the fictitious distance. That is what is chosen here. So these are some. So computational domain, and that's just what I mentioned here. We have some amoeba-shaped computational domain and how many points are taken. So that's how this amoeba is entirely in this negative 1-to-1. So we can apply the Chebyshev polynomials in here, and so we can complete this. This is the so here on the right side you see the error plot. So that's what I'm saying here. So how many Chebyshev nodes we take? 10, 12, 14, 16, 26, 28. So what is the accuracy for the Cassini amoeba? So as you see, as the number of Chebyshev nodes increases, the accuracy goes up. And after the certain point, of course, you will not get the same type of accuracy. So there are many things that we actually work with. So we get the accuracy. So here it goes up. So that's the accuracy we see we used for. I think this is for the. I think I have mentioned here. This is for the Schroen equation or something. Yeah, it doesn't show up here. I don't know why. But here, that's what I'm saying. Like here, we see here what is the exact solution, because we don't know for sure what is the exact solution. So we take the optimal radius and then that's for the Poisson equation. And this is here you will see here MFS and CT, because I used the two different methods, collocation trace method and then method of fundamental solutions. So this is and similarly, would that accuracy continue to if you have different partial different equation? So this is for modified Helmholtz equation, that's another type. And here, of course, we use another computational domain, starline domain here. So in this case also we got pretty much the singular, which actually is -12, -14. So that is for the method of fundamental solution, and that's the computation. Collocation trace method. Those are the two different. But even in those two methods, when we compare, we get a very similar type of accuracy. That is also another part of this test, having numerical accuracy in a different domain. So this is another one, and of course we use the different boundary conditions, because that is another part which we use the boundary conditions, and then here we have in the computational domain the testing, and in this case also, as you see here, I think here we use only the method of fundamental solution. So we need to square a millibar, so we go up to 30. How many will you go to? 15 minutes more. Oh, 15, 20. Okay. So another thing is just like a surface plot. This is another test function. Actually, if you're wondering what this is, basically they wanted to test their numerical methods. Actually, what the numerical method on different functions. So this is another standard test function. That's what we call Frank's test function. And these are the 4 test functions, and we apply. Actually, we performed our numerical experiments, Chebyshev polynomial scheme, on this test function also. And in this case also, we actually got pretty satisfactory numerical accuracy. So that's what we call the high accuracy, compared to the other. And then, for example, here, this is the maximum absolute error for the first test function, 1, 2, and 3. And so in this case also, we have some numerical point here, which is actually measure, and we put that over here. I think everything is not clear, of course. So this is I think this is another example, numerical experiment we did for the biharmonic. And here we have CPS, MFS, and in the biharmonic case, of course, this is the biharmonic operator here, and we have got pretty much good result. Not as good as the previous one, but still, this is considered as pretty. So with the help of those numerical experiments on Chebyshev polynomial schemes, so what we concluded actually is that the process, the method was not as complicated as the other methods. We have not, compared with the other one here. So the method was not complicated. That's what we said. Simple and direct, highly accurate. to solve elliptic partial differential equation and the constant coefficients. So it perfectly works for irregular domains as well, and higher degree PDE as well, like fourth order. And I think we already did this variable coefficient as well. That's another paper would be. But we are still working on time-dependent problems, and we have already solved in Cauchy-Neagle equation, one kind of, and axisymmetric problems using this method. So there are some things we already worked with, and then some are still working on this. So I would like to thank actually my co-advisor, Dr. Tien, and then my colleague, Dr. Manishan, for their support of this work. Well, this is what I wanted to present. Thank you all.
So thank you, Dr. Ghimire, for your presentation. It was really good and enlightening in the sense that I came to know that mathematics can be used to recreate the image. That was quite disturbed big one, so that was a new thing to me. So thanks for that one. So as a part of appreciation gesture, we have Troy swag bags. So he has a letter of appreciation and some Troy's goodies. Thank you so much. I will hand over to you. We have